Well, good morning, good afternoon, good evening, wherever you are in the world, regardless of time zone. I'm Bill Regsdale, the founding president of the Fourth Interest Group and the author of the Fig Fourth model. But that is back from ancient history, back in the Stone Ages of Fourth in about 1978, 79. Today, we're going to discuss some simple sorts that are done using a matrix sublanguage that I developed using Fourth. And we needed a simple sort to support that language. So I needed a simple sort that I could use for, let's say, 10 to a low hundreds of rows, primarily for early testing and exploration. I realize that more complex sorts are suitable for larger matrices. Get up above 100 or so, the sort times become quite large. So I explored 4 bubble sort strategies, which I'll present today. First was a full sort of all rows, which takes an n squared time, depending on the number of rows, because say with 10 rows, we sort 10 rows 10 times or make 10 passes through, a total of 100 comparisons. So that's our n squared. A simplified version of that is to support on all rows, but with an early exit. Another one that was an improvement is a diminishing sort. In this case, it's n squared over 2. We'll discuss that in a moment. And then finally, we have a diminishing sort with an early exit, which is n squared over 2 with a little bit shorter time. The bubble sort is often used as a cleanup after more complex sorts. Its time, as we mentioned, increases by n squared. So every time you add a digit to the number of rows, for example, if you go from 10 to 100 or 100 to 1,000, the sort time will increase by a 100-fold. One advantage is that you can sort in place with almost no temporary memory. There is a side transient memory for holding capacity for one data entry, one line entry. But the advantage is that you can do this it'd be suitable for use, say, in a embedded controller where you have very limited RAM memory. So the general method on this is that you scan downward by row, examining each column value. If the target value in the column is larger than the subsequent or the next following column entry, then you exchange the rows. This way, the smaller entries go toward the top, the larger valued entries go toward the bottom, large values sink. Another advantage of this is that it preserves the order of sorted columns. So if you sort on a low priority column first and then sort on a high priority column, the low priority column values will be remained in their sort. Each scan can cover one less row, as the last row is known to be the largest value. This allows us for a diminishing sort. So remember, if you make one pass through the entire matrix, the lowest value is guaranteed, the largest value is guaranteed to be at the bottom of the matrix. So there's no need to sort. The next row can be n-1 rows covered. Here's an example. It's a matrix constructed of floating point numbers. They're randomly generated. So it's a 3 by 10 matrix, and we're going to sort. Initially, it would sort on column 3. So we see the values have, after sorting, are going from 1, 2, 4, 5, 6, 7, up to 9. Now sorting on column 2, we see the column 2 values are in order, starting at 0, going through 2, 5, 6, 7, 8, ending in 9. But notice in the green circle, the subvalues of the second row for 8 are maintained in their original order, in their sorted order as 4, 7, and 9. So we see this nice extra capability is of maintaining those sub rows in sorted order. Here's the code that actually accomplishes the work. We see that the row exchange code starts with the X curly brace, which identifies the matrix location. C is the column we're sorting on, and then R1, R2 are the two rows that are going to be examined for an exchange. And the initial input values of X curly brace and C are maintained after the exchange has taken place. It's done in 3 stages, as you might think. The first one is to pick the from row, and it is translated or transported into a transient matrix. The transient matrix in this case is row 0, column 0, and we use C move. So once we've determined the size of the bytes to move, the whole row is moved into the transient matrix. The second section, which is begins 3-pick with the from, takes the ultimate destination row and moves it back to the very first row. And then finally, the temporary value that is in transient is moved to the final position. So it's a 3-step process. We do a from, we do a transient, and we do a to. This does the sort through the matrix, one pass all the way through. So it's looking for to move the higher values toward the top. But remember, they only move one row at a time. So it is very inefficient because every row has to be examined every time. So the one-pass routine takes the X curly brace, which is the matrix address. The C is the column we're sorting on. And in this case, we're sorting through a given row. Initially, we sort through all the rows, and then we can arrange it to be a diminishing sort after that. So 1 plus 0 sets up our do loops. And in the case then, the 2 values are extracted. The over I2 pick, the double curly brace fetch gets us one of the floating point values. The over I plus 1 is the next value in the matrix, and its floating point value is extracted, and then the F greater than sign selects is an exchange to be made or not. If an exchange is to be made, the if sequence with the I and I plus 1 specifies the row exchange. And so this handles selectively one row pair exchange. To make one pass through, we use the curly brace bubble. We give it again the X value in the column we're sorting on, and this will then scan down repeatedly over the entire matrix. Initially, we give it all 10 rows to begin with, so it will sort repeatedly over all 10 rows. And we see down in the do loop, we pick the target row that we're starting on. We do one pass, and then the -1 plus loop gives us the diminishing loop value. So every time through this loop, we go one value less. And you see the open transient and closed transient specifies the one intermediate row that is used on a scratch basis. So here are the results we find. For 10 rows, the sort time is less than 1 millisecond. With 100 rows, it's 40 milliseconds, which is quite reasonable. And with 1,000 rows, it increases to 4.4 milliseconds, which is probably useful and appropriate, with a fairly moderate amount of delay. If we apply the early exit, this means that once a pass-through is made through the entire matrix with no exchanges made, then if we terminate a little earlier, for 100 rows, it ends up being a 34 millisecond on average. For 1,000 rows, it improves the time from 4.4 seconds to 3.7 seconds. And remember, this early exit time is subject to some variation because it really depends on the randomness of the sort and how soon the early sort meets its final condition. By Instead of doing an n squared sort, we're now doing an n squared over 2. It's a diminishing sort so that every pass through the matrix is 1 row less. For 100 rows, we see it improves the time to 32 milliseconds. For 1,000 rows, it goes from this 4.4 range down into, say, 3.8 seconds. And in this case, I did a 10,000 row sort. Notice for 10,000 rows, there are 100 million comparisons made. There are 100 million comparisons, 10,000 squared. And this is accomplished in somewhere between 5.5 and almost 7 minutes. So it's quite a bit of time for, fairly large matrix. Finally, applying the decreasing sort with an early exit, the sort times improve down into the 16 to 32 millisecond range. The 1,000 sort goes down into the 2-3 second range. And I assume for the 10,000 sort, it would probably go down to about the 4-minute range. But still, 4 minutes is quite a significant period of time. So what would we do in the future? Well, we should move to more complex sorts, which improve the sort time. The classic models are the shell sort and the insertion sort. And as a look ahead, I'm actually doing continuing work to transition over to an insertion sort. I would offer an editorial comment that the sorts in Excel are fantastic. There are hundreds and thousands of sorts done in fractions of a second. That is, sorting over hundreds of thousands can be accomplished in fractions of a second. I've done sorts of 2,000 and 3,000 rows, and the time is barely noticeable, probably less than 1 second. So my hat's off to however Microsoft is doing that. I suspect they use large amounts of short-term memory, at least 1 or 2 complete images of the matrix to accomplish that savings. So that concludes my presentation for today. I appreciate your rapt attention. Thank you so much. And now I'll return back to Mission Control.